So it's my pleasure to start the working group introduction, and I'm currently the chair of the reliability group together with Stefan Arnson. My presentation is split basically in two parts. First is a review of what we have achieved in phase 1 of the ISG, and then I also briefly glimpse at what is happening at the moment. As a result of phase 1, we have published the report on resiliency requirements back in January this year. And after having set the scene by some high-level requirements, we did a use case analysis for various reliability and availability use cases in the NFV environment. We also had an analysis of what have been defined as service availability levels at the moment for telco services, and try to fuse them together and understand how this translates into requirements for an NFV environment. Based on these analyses, we identified a set of technology requirements that are a prerequisite to build a system with high availability and resiliency built into the system to deal with various challenges which might affect the operation of the services. Amongst others, we have considered functions like migration within and across system boundary domains of virtual network functions. We have looked at failure detection and reporting of such failures across the various layers of the architecture. We were looking at prediction mechanisms that help us identify what impeding failures might be affecting the system soon. How to prevent those and how to remediate and recover from those failures to come back to normal operation as quickly as possible. And finally, we have been looking at mechanisms that deal with increased load and the situation where we cannot distinguish between overload situations and call blocking conditions, be it by legitimate unusual high traffic or by cyber attacks that might target the system to affect the operation. Then the final chapter of the Year 1 report is about engineering and deployment guidelines, which should help the engineers in the design and implementation phase to bring out to develop a system that can meet the high reliability requirements the operators have for such a system, and also to ensure the service availability during system operations. The report also has an annex on an extensive set of various faults and challenges that might impact the NFV system's resiliency, and give some indication on for the engineer for what challenges to protect the system, be it by preventive measures or be it by building in systems that remediate such failures in order to come back to normal operations. Having seen this overview, I go into some details of what we have documented in this report. One of the results you can find in the document is a set of resiliency principles, and which we have characterized in 4 different groups, and you see an excerpt of those different principles here. The categories are prerequisites, trade-off, resiliency enablers, and resilient system behavior. With these principles, we envisioned to help guide the engineers to design and implement an NFV system from the beginning, with resiliency being a prime member of the system design. And the prerequisites should be followed in order to avoid a set of mistakes or system limitations that would jeopardize the system resiliency. Obviously, as we do not have endless or unlimited resources to spend on resiliency, we have to deal with trade-offs that need to be respected and should be explicitly called out, as we have done in the second category. One of them, obviously, is if we would like to build a super high available systems, preventing almost all threats and challenges and being protection on all levels and layers. That would consume endlessly money, increase system complexity, system operational complexity, and so forth. So this trade-off needs to be recognized by the system engineers. Then we have a set of what we call the resiliency enablers. This is a set of different mechanisms grouped under this principle category that helps us build a highly available system due to the new capabilities of a cloud and NFV environment. One of those is the ease of getting additional resources rapidly deployed to the system, and by that, these means protecting the system from outages. And last but not least, we have a set of resilient system behavior principles that lead to a system that ideally autonomously can react to certain threats and challenges to the system and prevent the VNF from not providing the service which it was designed to provide. Based on these principles, we looked at a fault management cycle and started with the failure prevention mechanisms. As I already said earlier, one of the obvious things is that if we have a mechanism, an underneath mechanism that allows for dynamic scale out, like the cloud provides to VNF, it might appear that the system by itself is already resilient to overload situation and call blocking situations. But as we have shown in the document, that's of course a remedy for some type of overload situation, but it is not a sufficient mechanism for any kind of overload situations. Failure prediction, there we have identified a set of different metrics which we want to measure in order to assess if there's an impeding threat to the system which might challenge the system operation and would allow for mechanisms to be initiated to minimize the impact to the system or at least to the service user. And last but not least, we looked at various types of failure containment on the various levels. As we will see failures in the system, we need to ensure that those failures are contained on each of the levels, be it by preventing propagation across level boundaries and limiting the notification storm across level boundaries. But still being aware that even if we have built preventive mechanisms into the system that provide the capabilities to reduce the likelihood of a challenge degrading the provided service, we are still aware that we cannot forecast any type of different challenges, nor can we build a system to protect from all of those challenges. So we need an active management cycle, which we have built in three stages, namely detection. Once the service is not providing its normal operation anymore, we need to detect what is going on and identify what happened to the system. Then ideally we apply a quick remedy which brings the service back into an acceptable service stage again. And after having removed the actual failure from the system, we call that stage recovery, where we are back to normal operation. Normal operation in that regard means that the service provides operates the service as it was designed for. And last but not least, we have started looking at a failure correlation mechanism. Here we identified that having the different layers which we recognize that we need to have early correlation of those information types to avoid information floods, and that is especially challenging as we are talking about a multi-vendor environment. This we have also made the hot topic of reliability in phase 2, and currently we start working on that type of correlation functions and see how far we can get with that. This brings me to the phase 2 of reliability, availability, and assurance working group, which we have started beginning this year. We have started off with the scope that we, of course, want to look at different specification areas for reliability and availability. We're still investigating different enhancements which help the engineers to build a system in a way that it leads to a highly available NFV-based network service. We analyze reliability and availability techniques that might be helpful for our environment. We respond to requests from other working groups if they ask for new or current features to be supported in the context of NFV, especially touching on reliability and availability mechanisms. We provide guidance, as we did before, be it on mechanism validation, assurance, and SLAs, but also on the interworking with physical network functions in our area. And last but not least, we are driving the necessary contributions in other working groups, if applicable, to have a close alignment between the various work items in our group and other working groups from the beginning. So the work items we have running at the moment is REL 002 to REL 005. REL 002 is the scalable architecture for reliability management report. This is very close to finalization. We intend to give working group approval for this work item here in San Jose. And what we have set out with this work item is to develop an understanding on how current cloud environment techniques make a system highly reliable, and what of those are applicable to an NFV environment. So the scope of this work item is to look at different type of conditions where such scalable methods apply to, like resource failures, be it on the physical resources or the virtual resources. All of those could be compute, network or storage resources, or again bursty traffic conditions where we see a rapid increase in load, which might call for a scale out of the system. Based on those analysis, we describe scale-out techniques for instantiating new VNFs for such conditions and assess how well they fit to meet the requirements. We underpin these techniques by corroborating lab results, which we have documented in the annex of the work item. The second work item which we are running at the moment is the models and features for end-to-end reliability. There we study and develop reliability estimation models for the NFV environment and assess the system availability during the various stages of the VNF lifecycle. We have started with introducing software reliability as we know it from literature, and then we apply this to the different components of the NFV architecture and how the involvement of the various management and orchestration functions, be it for fault management, failure detection, etc., fits into that. And for all of those different mechanisms, we especially look at the lifecycle operations, the impact of load, software upgrades, scaling mechanisms, and how these different functions affect the reliability and availability mechanisms which we have deployed. And based on those, we then develop the availability models that helps the operator assess the current availability he can guarantee to his customers. The third active work item at the moment is the active monitoring and failure detection work item. There we are developing active monitoring mechanisms for VNFs, the NFVI and the services, as well as mechanism for detecting failures currently affecting the system operation. The scope of this work item looks at various testing functionalities which we build as VNFs and hence can be integrated and orchestrated like ordinary VNFs into the service function chain with the mechanisms provided by the IFA working group. Based on those findings, we envision that a system can then detect failures and initiate the appropriate recovery actions based on the results from the active monitoring methods and provide the resiliency required for this VNF deployment. And the last work item, which we have just started a couple of weeks ago, is REL 005 on the quality accountability framework. The goal of this work item is to develop a report that promotes the development of capabilities by which VNFs, NFV infrastructure, and MANO can enable rapid and reliable root cause analysis of service quality impairments, corrective actions, and SLA management. So the scope is to identify high-level roles, service boundary, and associated NFV reference points, and the quality-related responsibilities to enable rapid root cause analysis and corrective actions. From the beginning, we want to align these with the roles which have been defined in Team 4's SLA management service delivery relationships, as well as with the PNF quality measurements, namely TL 9000 service outage measurements, and apply them to the VNF on a side-by-side quality comparison. And that concludes my report on the reliability working group.